Hi everyone, I'm Zhipeng from Carnegie Mellon University. Today I would like to introduce our work on achieving 100 gigabit per second intrusion prevision on a single server, which is equipped with an FPGA-based SmartNIC and a multi-core CPU. Intrusion detection and prevision system is a critical network application to protect the security of our network. This type of system is usually deployed at the gateway of our local network to identify and prevent the network threats from the internet. This is achieved by checking the network packets, including the packet payload, against the large numbers of complex rules or signatures. And since almost every single byte of a network traffic will be checked against tens of thousands of rules, intrusion detection and prevision system is considered to be one of the most compute-intensive network applications. And due to the intensive compute requirement, there is a huge performance gap between today's LAN rate and the intrusion prevision system performance. This figure shows the network LAN rate evolution. Today, it is common to see 100 gigabit per second network in large enterprise. In contrast, the state-of-the-art software intrusion prevision system performance is about 1 gigabit per second per CPU core, which is already 8 times faster than prior work. Nevertheless, it is still 2 orders of magnitude slower than today's LAN rate. To give you a concrete example, we evaluate the state-of-the-art open-source software intrusion prevision system called Snort, which is equipped with the latest high-performance Hyperscan pattern matching library. This figure shows the number of cores needed to reach 100 gigabit per second. The x-axis shows the empirical traces we have evaluated, and the y-axis shows the number of cores needed to reach 100 gigabit per second. Note that the core number here are extrapolated from the single core zero loss throughput we measured. And this extrapolation assumes ideal scaling. As we can see that some traces will require hundreds of cores, but the other traces will require much more number of cores. Overall, this approach will require 4 to 21 servers and 1 to 6 kilowatts. Dedicated 4 to 21 servers just for this intrusion prevision purpose is not a cost and power efficient solution. In this work, we propose Pigasus, which is a 100 gigabit per second intrusion prevision system that implemented on a single server. Our end-to-end system consists of an FPGA-based SmartNIC, which can process the network traffic inline, and a 16-core CPU. Now let's take a look at the comparison between Pigasus and Snort. Here, we also evaluate our end-to-end system using the same set of rules and traces as Snort. The orange bar represents the number of cores needed to reach 100 gigabit per second for Pigasus. It's important to point out that Pigasus numbers are real core count. They are not extrapolated numbers as shown for Snort. As we can see, Pigasus uses 100x less cores than Snort consistently across all the empirical traces. And in the worst case, we only need 14 cores. So our end-to-end system only uses one 16-core CPU plus an FPGA-based SmartNIC. And the overall power consumption is 2 orders of magnitude less than Snort solution. So what's the secret sauce behind this 100x improvement? As I said earlier, we use FPGA in our system. However, simply following the traditional FPGA acceleration scheme would not give us this 100x improvement. In this work, we propose FPGA-first architecture, which is a fundamentally different FPGA acceleration scheme to make the 100x improvement possible. Before I introduce FPGA-first architecture, let's take a look at the traditional FPGA as offload acceleration scheme. And in this scheme, packet comes into CPU first, and then CPU parses the packet and reassembles the packet into contiguous byte string. Then CPU offloads a particular task to FPGA, for example, the multi-stream pattern matching in this case, where the packet is partially checked against tens of thousands rules. If a packet does not partially match any rule, then this packet is an inefficient packet and will be forward out. If a packet partially matches any rule, then this packet is a suspicious packet and will be further checked by a module called phone matcher on CPU. In this scheme, CPU is still the main processing unit, and the FPGA is the offloader. However, this approach will not give us 100x speedup. The main reason is that there is no single dominating task anymore. Especially, Hyperscan has made the multi-stream pattern matching task 8 times faster than prior work. This figure shows the performance breakdown of Snort plus Hyperscan. The x-axis is, again, the different empirical traces. The y-axis is a fraction of CPU time each task takes. As we can see, there is no single dominating task. And based on Amdahl's law, accelerating a particular task can at most give us about 2x end-to-end speedup, assuming this task takes 0 time to execute on FPGA, and there is no communication overhead between FPGA and CPU. Clearly, we will not get 100x speedup using this scheme. So the key design decision we made in Pigasus is to invert the traditional offload scheme. We call this new scheme FPGA-first architecture, where the FPGA is a main processing unit and CPU works as an offloader of the FPGA. This figure shows the FPGA-first architecture used in Pigasus. The majority of the tasks are mapped to FPGA, and only part of a phone matcher is mapped to CPU. The packet comes into FPGA first and may or may not reach CPU. Indeed, we have observed that among all the empirical traces we have evaluated, on average, about 95% of the traffic can be processed entirely on FPGA, and only 5% of traffic will be considered as suspicious packet and thus require full match on CPU side. By processing the common case entirely on FPGA, we significantly reduce the workload for CPU, and thus reduce the number of cores needed to reach 100 gigabit per second. However, it is very challenging to realize this FPGA-first architecture because of limited fast memory on FPGA. Even though we are using a pretty high-end FPGA, the amount of fast on-chip memory, which is called block RAM or BRAM, is very limited, only about 16 megabytes. But we would like to map almost everything on one FPGA. This will not fit if we directly using existing FPGA modules. For example, if we just using existing FPGA-based flow reassembly and FPGA-based multi-stream pattern matching module, they will require more than 87 megabytes of DRAM, far beyond our 16 megabytes capacity. So the challenge here is how to fit almost everything on one FPGA. To just recap, the first secret sauce of Pigasus is to use FPGA-first architecture, which makes 100x improvement possible. However, it also introduces the memory challenge of fitting almost everything on one FPGA. And to tackle this problem, we proposed a couple of ideas. But in this talk, I will just focus on one of the algorithms to address the memory challenge, which is hierarchical multi-stream pattern matching. Please refer to our paper for other ideas like flow reassembly and memory resource management. So the goal of multi-stream pattern matching is to check the packet's payload and port number against the tens of thousands rules in one pass. Here I'm showing you an example rule. In Snort, the multi-stream pattern matching is responsible for checking the header field of a rule and the faster pattern field of a rule. The rest of the fields, including the other stream pattern or regular expressions, are checked by the flow matcher. It's important to point out that if any field is a mismatch, then this rule will not be a match. For example, if the faster pattern is not a match, then it is safe to ignore the entire rule. Pigasus multi-stream pattern matching is different. We check the header, faster pattern, and as well as the other stream patterns, which we call non-faster stream pattern. This part was checked in Snort flow matcher initially, but we found that it is dominating the flow matcher runtime. So we decided to map this matching logic on FPGA to further reduce the load of CPU. Now let's look at what are the design options to map multi-stream pattern matching on FPGA. The state-of-the-art FPGA-based multi-stream pattern matching uses state machine-based approach, which will require 23 megabytes of BRAM if we want to map all over tens of thousands rules. The Snort Hyperscan software algorithms use a hash table-based approach. However, directly mapping that algorithm to FPGA will take 25 megabytes of VRAM. So none of these algorithms meet our requirement, as we only have 16 megabytes of VRAM in total, and that is shared by all of the components on FPGA, not just the multi-stream pattern matching. Pigasus multi-stream pattern matching is inspired by Hyperscan algorithm. We also took the hash table-based approach. However, we are able to complete more work, but only using 3 megabytes of VRAM. In this talk, I will not show the details of how we implement and organize the hash tables. Instead, I will explain the high-level ideas of multi-stream pattern matching design. Pigasus utilizes the performance and memory trade-off in FPGA design. To support high performance on FPGA, usually we need to leverage the data parallelism, where we can process more data in parallel. This requires creating multiple replicas of the matching data structure, such that different data can be checked simultaneously to increase the overall throughput. However, this will lead to more memory consumption at the same time because we have made more replicas. That is part of the reason that the multi-stream pattern matching is very memory consuming. Our key observation is that in practice, there's no need to keep up with 100 gigabit per second everywhere. As I will show later, some of the subcomponents can work at lower speed. And because of that, we can use less memory when lower performance is allowed. So our key idea in multi-stream pattern matching design is to use hierarchical filters with reduced replicas at each layer. Now let me show you how it looks like. Pigasus multi-stream pattern matching has 3 stages. The first stage is responsible to handle 100 gigabit per second of data. And thus, we do need to create enough numbers of replicas to keep up with the speed. But after the first stage, the majority of the bytes in the traffic will not generate any potential matches. As a consequence, the following stages do not need to run at 100 gigabit per second on average. For example, the second stage is a header matching stage, which only needs to keep up with about 23 gigabit per second. And the last stage, non-fast stream pattern matching stage, only needs to keep up with 11 gigabit per second based on our profile of empirical traces. Thus, we can reduce the amount of replicas of expensive features. For example, the non-fast pattern stage only needs 16 replicas. So in the end, we only need to push about 5 gigabit per second of traffic to CPU to significantly reduce the amount of work that to be handled by CPU side. So now let's take a look at the evaluation results of our end-to-end system. I have shown this figure in the beginning of my talk. Here we test both Snort and Pigasus using the same set of rules and traces. The x-axis represents the different empirical traces we have evaluated. The y-axis shows the number of cores needed to reach 100 gigabit per second. So the lower, the better. The blue bar represents the Snort core numbers, which is extrapolated from the single core performance we measured. The orange bar represents Pigasus core numbers, which is the actual core count when Pigasus handles 100 gigabit per second traffic without any loss. Again, we can see Pigasus uses only a handful of cores, which is 2 orders of magnitude less than Snort. So what's the benefits we can get by saving hundreds of cores? The answer is lower power and a lower cost. Here I'm showing you the power consumption of Snort and Pigasus. This time, the y-axis is power instead of cores. As we can see, Pigasus uses 2 orders of magnitude less power than Snort. We also estimate the total cost of ownership of both Snort and Pigasus. The total cost of ownership is calculated as the sum of capital cost, which is the hardware cost itself, including the CPU cost and FPGA boards, plus the energy cost, assuming 3 years of lifetime. Snort total cost of ownership is about $36,000, where Pigasus total cost of ownership is less than 1/3 of that. And this saving of Pigasus comes from both the capital cost and as well as the energy cost. To conclude, Pigasus is able to support 100 gigabit per second on a single server, saving hundreds of cores and thus only consumes 1/3 of the Snort approach cost. The key design decision made in Pigasus is the FPGA-first architecture, which makes the 100x improvement possible. However, at the same time, this also introduces the memory challenge. And to address the memory challenge, Pigasus proposed a couple of ideas to efficiently use memory. And in this talk, I only explained how hierarchical filters makes the multi-stream pattern matching more memory efficient. And please refer to our paper for the other ideas. Pigasus is open source now, and welcome to try it out. Thank you.